This is a follow-up video to the one we did earlier on forces in motion, and this is going to focus more on work and energy. So let me just put you on full screen so you can see the slides more easily. Okay, so in GCSE, forces, work and energy are interrelated, so it's a good thing when you're revising to revise the topics together. Okay, in Edexcel IGCSE, for example, forces and motion is topic 1, work and energy are covered in topic 4, and then some of the energy involves thermal physics, so there's a link between thermal energy and solids, liquids and gases, which is done as unit 5. So all the topics interrelate, and when you're revising you will see this, and when you get into year 11 the questions will expect you to know things from year 10 as well. So whenever you're revising you probably need to revise the year 10 topics to be able to answer questions in the year 11 topics. So these were this is the AQA list of equations, and I went through this in the forces and motion video that I just uploaded earlier today, and it also involves springs. Yeah, so when you stretch a spring you're doing work on the spring and energy is stored in the spring. Okay, and here you got the equation for work done. So if you lift a weight, for example, against gravity, you're working against gravity and you're increasing its potential energy. So work done against gravity becomes potential energy gained because the weight, which is mass times gravity, which is the force, goes up a distance which is h, and you will see when we do that the work done against gravity is also equal to potential energy gained, and potential energy is kind of energy stored when you do work against gravity and lift something higher. Okay, so when an object is moved by force, we say work is done on the object by the force. Okay, this is called mechanical work. Yeah, so remember when you did the energy unit, there were different types of energy transferring from one energy store to another. So if you're working against gravity, you're transferring the work into the potential energy, gravitational potential energy store. Okay, the force transfers energy to the object by means of mechanical work. Okay, so gravitational potential energy transfers is the change in gravitational potential energy. So it's the energy stored in an object because of its position in a gravitational field. Usually it will be the Earth's gravitational field. So you need to know what the gravitational field strength is. For Earth, it's given as 10 newtons per kilogram or 10 meters per second squared. Okay, so the equation for the change in gravitational potential energy, which is measured in joules, will be equal to the weight, which is mg, times the change in height. So this will be mg times h. Often it's written as mgh. Yeah. A symbol used often for a change will be used as a delta. Delta energy equals weight times delta h. So if you see a delta sign, it looks like a triangle. Okay, that means a change in height from start to finish. Okay, so for example, if we want to measure the change in potential energy by lifting this 1 Newton up to this shelf, if it moves up 1 meter, the weight is 1 Newton, yeah, and the height gained is 1 meter, so it will just be 1 joule, yeah. So the first one is 1 joule. If we now lift 2 newtons to this by 1 meter, remember you should really measure from the bottom of the weight to the bottom of the shelf where it's going to sit on. So if we lift these 2 newtons up exactly the 1 meter, what do you think the potential energy change will be in joules? So it's 2 newtons of weight now multiplied by the change in height, which is just 1 meter. So it should be double what we did in the first place, so it'll be 2 joules. Okay, now if we lift the 1 Newton, like in the first question, but not to the first shelf, but to the second shelf, which is another meter higher, the total height gained will be 2 meters, and now it's going to be equal to 1 Newton times 2 meters. So this is a very simple maths, and it will again be 2 joules. So work done against gravity is a change of gravitational potential energy. And if someone knocks those weights off the shelf, they will lose their potential energy. So the energy will be transferred from the gravitational energy store, and it will turn into kinetic energy as it speeds up and falls to the ground. Okay, so energy stores are when something has the energy within it or because of its position in a field. Okay, hope that makes sense to you. So we won't always be given the weight. So sometimes we'll be given the mass, and you've got to work out the weight using the gravitational field strength. Okay, now they could ask you to compare work done on the moon, for example, with work done on the Earth. So if we did exactly the same experiment on the moon, you wouldn't be able to use the weight on Earth as the m times g. You would multiply the mass not by 10, but by whatever the gravitational field strength is for the moon, which I believe is 1.6 to 2 significant figures. So this is the official equation for potential energy or energy potential, and by that they mean gravitational. Okay, so you need to know these symbols as well. If something falls, the mechanical work is actually done by the gravitational field. So there is still work being done. It's just that you don't have to do it mechanically yourself. It is done mechanically by the gravitational field. In other words, the Earth is doing the work to pull something off the shelf. Okay, so the energy is measured in joules. Mass must be measured in kilograms. G is 10 newtons per kilogram for Earth, and different on different planets and moons. And height always in meters. So make sure you stop the video, make sure you got these notes written, and when you come to revise, I highly recommend you getting the CGP books, those revision books where they go through every topic. Okay? But of course they can't speak to you, so I think these videos will allow you to listen as well as make notes. So remember, you can watch these videos slowly or fast, and then you can pause them whenever you want to make sure you've got a good set of notes and a good understanding by listening clearly. Okay, so kinetic energy is the energy store within a moving object. So any moving object is said to have energy stored in it in terms of its motion. So movement energy is called kinetic energy, and it's equal to half times the mass times the velocity or speed squared. Okay, so you just need to know this equation, and you need to be able to put numbers in to get the answers out. Once again, the energy will be in joules, the mass will be in kilogram, and the speed would be in meters per second, but you need to square the speed. Okay, that's why when the car was trying to brake, if you double the speed, the energy is not just doubled, but it's quadrupled, because the speed squared means that the energy isn't just doubled, it's doubled squared. So double the speed, you have 4 times the energy. So if one car is traveling twice as fast as another car, and they're identical vehicles, they have the same mass, the one that's traveling twice as fast has 4 times the energy, and therefore it would take 4 times as much work to slow it down. Okay, so that's why speed kills, is what they say. So the next kind of energy you could have is elastic potential energy, and a catapult, if you stretch the elastic bands or the elastic material that is designed to eject a mass with velocity, the elastic bands contain elastic potential energy when stretched. Okay, same thing happens in the sport I play, which is squash. The squash balls are made of rubber, and when they're squashed, they become hot and they bounce more. So they store some kind of energy in the material they're made of. Okay, Work is done on an elastic object when its shape changes and it stores elastic potential energy. And you did this when you studied Hooke's law in year 9, and then you also need to remember that and use it for your GCSE revision notes because it comes into forces and energy. Okay? So elastic potential energy. Work is transferred mechanically by work done, by stretching it. So it's mechanical work. It's work done is force times distance. And that amount of work in energy is then stored in the material, the elastic material that, for example, here, rubber has the ability to store elastic potential energy. Okay? In the GCSE Edexcel, they don't expect you to know the equation, but it is half kx squared. Yeah, so it would be the area under the force extension graph, and the steepness would be the elasticity of the material. Yeah, for a rubber material, it's not usually a straight line. It's not directly proportional. Okay, it's actually more of a funny S-shape curve. All right, but the energy stored would still be the area under a force extension graph. So this is revising Hooke's law for you. Okay, an increase in length leads to energy being stored elastically in a form of potential energy. You can then release, say you want to catapult a mass, you can release that elastic potential energy and turn it into kinetic energy, which is what a catapult does. Okay, so the next thing that we studied when we did forces in year 10 was that as well as having work and energy, a moving object also has momentum. Please ignore the reference P2.3. It's, I think, from AQA, that syllabus number. So for Edexcel, it's a combination of units 1 and 4. 1 and 4 is work, energy, and momentum. Okay? So momentum is a vector quantity which is possessed by any mass which is moving. Yeah? If it's not moving, the momentum is said to be 0. So the tendency of an object to keep moving in the same direction, it can be called momentum. When you have momentum, to change your momentum, a force is required. So the bigger the momentum, the more of a force is required to change your momentum. And this kind of goes along with Newton's first law. So an object with high momentum will be more difficult to deflect or slow down than an object with low amount of momentum. So things that affect, like kinetic energy, things that affect momentum are mass and velocity, but you can see in momentum there is no squared component to the velocity. So momentum is simply the mass times the velocity. Okay, so a 40 kilogram person running at 6 meters per second, you just multiply the mass in kilograms by 6 and you'll get 240. So the answer will be 240 kilograms meters per second. Okay, so momentum is used when there is collisions. So this is an area of physics. In Edexcel, this will only be examined in the international exam in paper 2, so it's for physics IGCSE students only. If you're doing double award combined science, they will not expect you to do the conservation of momentum parts of the syllabus. So it says, so long as no external forces are acting on the objects involved, the total momentum stays the same in both explosions and collisions. The way I always explain it is an explosion first. So if you've got a hand grenade and you just place it on the table, its momentum is 0. But if somehow the hand grenade goes off, it fires out in all directions bits of itself, and momentum in opposite directions will be equal but opposite. So if you think of a piece going to the right and another piece going to the left, the amount of momentum going to the right and the amount of momentum going to the left in a straight line, diametrically opposite, so exactly opposite. The amount of momentum to the right will be positive. The amount of momentum to the left, mathematically, we always count as negative. So one bit will go in terms of positive momentum, and one bit will go in the direction of negative momentum. If you think of it simply as right being positive, left being negative, like on a graph. So the explosion at the beginning had zero momentum, and if you do that in every two directions, you can prove that the total momentum after the explosion, because it's a vector quantity momentum, is zero afterwards as well. Same thing happens just after a collision. Yeah, it's difficult to see because then frictional forces take over very quickly. But for example, on an ice rink, or there's that Olympic sport where they kind of push kettles and they bounce off each other. Yeah, that's a good way of thinking about it. So the moment of collision between two of those objects on the ice, because the friction can be minimized, will explain this to you quite well. So when one kettle hits the other, one might become stationary, the other one takes away the momentum, and you could then assume that the momentum just before the collision must be equal to the momentum just after the collision. Okay? So explosions of momentum. So the mass of object A times the velocity of object A will be equal to the mass of object B times the velocity of object B. I think we can't see the rest of the writing. It's gone off the slide. I'll have to go and correct that. But I won't be able to do it in time for this video. So it's really what I explained to you. So these are not the best graphics to explain it, but if you could get these vehicles to have motion so you could see them, it would be easier to understand. I have another PowerPoint where I can show you this more clearly, and I will use that PowerPoint to make a video in the future, but this is the mathematical side of it. Yeah, so it's not clear from this what's happening, but I think what's happening here is like the two vehicles, this one and this one, I think it's meant to be A and B as it's written up here, but it's actually A and X. So if they both start off here and one goes to the left, that will be in one direction, one goes off to the right, it will be in the other direction, and because they're vector quantities, the velocity will be this way and the velocity will be that way. One direction will be negative, the other direction will be positive. If you multiply the masses by the velocities just after they interact with each other, either by an explosion or an explosive force where it sends them off in opposite directions, or a collision, then the momentum before must equal the momentum after. I don't think this is the best slide to learn it from, but if you go to your revision notes or watch my next video, which I'll try and do in the next week or so, you will see it makes sense. Okay? So here you got changing momentum. If two cars have a head-on collision, you also want them to be safe. So they design cars to crumple at the front, so the people inside, the inside doesn't crumple. It's a safety cage inside where the people sit, but where the engine is, the car is actually designed to crumple because that takes away some of the force of the impact, and it basically does work to compress the metal on both cars, and that increases the impact time. And if you increase the impact time, it will decrease the impact force. So these are important things. Yet again, I don't think this PowerPoint, which I've borrowed to make this video, is not the best way of explaining all this, and I will make another video on this to make it clearer for you. Okay, so that's the end of the introduction to forces, energy, and momentum. And I think really up to here is double science, and after this is physics only. So the physics only bit I'll make a separate video on the conservation of momentum. But I think up to here this PowerPoint works quite well. So if you found that useful up to this slide, please like, share, and subscribe so I know how successful these videos are. And the more likes and shares and subscribes I get, the more videos like this I'll make. Okay? So thank you for watching. Hopefully see you in the next video. Bye for now.